So think about the bobsled race, right? Think of like the last time you watched the Olympics, things like that. Bobsleds. It starts out with 2 people, 4 people running and pushing as fast as they can this big giant heavy cart, and then jumping in it and riding it down this little ice tube down to the bottom and trying to do it faster than anyone else. All right? So that initial force and distance where they're running at the beginning is the only work they're able to do to give themselves some energy. All right? And then that energy is all they have to get to the bottom. All right? So we're going to talk about conservation of energy. And this very much relates to a bobsled or skiing or riding a roller coaster or something like that, and having the ability to get through it without stopping and without, and with the appropriate speeds and things like that. So, just some of the main topics that we are going to get into is mechanical energy and its conservation. I'll define that in a second, and then problem solving related to that. And then we'll briefly touch on the ideas of other forms of energy, and then energy conservation with dissipative forces. Another word for that is friction. So we're going to start out assuming that there is no friction and there's nothing that can slow you down after you give yourself that initial push. But in reality, that's really never the case. Okay? So first thing, your online form is going to have 2 questions that you should already know the answer to. So I want you to go in and fill in the words. Please type all lowercase and with no punctuation. And preferably spelled correctly. Okay? But to have kinetic energy, an object must have what? And then to have potential energy, an object must have... All right? And I'm looking for one word answers. So think about the parts of the equation that differentiate the kinetic from the potential energy. You can also kind of think about what we did in that simulation. So, in an ideal system, so for now, this ideal system is frictionless. Frictionless. Energy cannot be created or destroyed. All right? Energy cannot be lost in any way, shape, or form. All right? It can only be transferred from one form to another. All right? So, mechanical energy is the total energy of a system. And it is made up of your kinetic energy plus your potential energy. All right? Again, this is assuming that there's no friction and there's no other way to convert it into other energies aside from the potential energy. If you let the object go and it starts falling, it starts to gain velocity, so that potential energy is slowly converted into kinetic energy. Okay? So, in frictionless ideal systems, mechanical energy never ever changes. Okay? So, to do problems with this, you should hopefully have already kind of seen the trend and the relationship between them. But since we know how to calculate PE and we know how to calculate KE, we can use that information to find mechanical energy, and we can use that to find any piece kind of anywhere on the path of an object. Okay? But some useful positions to keep in mind. There's the top, the bottom, and then everywhere else. Everywhere, mechanical energy is equal to kinetic energy plus potential energy. However, the top and the bottom have something unique about them. So if you look at the very top, your velocity is 0, which means what about your kinetic energy? KE is 0. All right? And then at the bottom, your height is going to be at a maximum. All right? So if you think about it, at the top, your mechanical energy is equal to 0 plus whatever your PE is. So at the very, very top, your potential energy is what makes up all of the mechanical energy. All right, this is assuming that your velocity is 0 at the top, which for the most part in this class, it'll be the case. However, there will be examples where it's already moving at the top, okay? Then if you look down at the bottom, we have a velocity, but our height is 0. All right, so if our height is 0, and they have y listed here, you're used to h, but y is the height axis on a graph, so that just means the same thing. But if our height's 0, potential energy is going to be 0. So mechanical energy is going to be equal to Ke plus 0. So at the very, very bottom, you have all kinetic energy because it's been completely converted from potential energy into very fast-moving kinetic energy. All right? Everywhere else, you're going to have both. Okay? The closer you are to the top, which energy are you going to have more of? Right? You should think that the closer you are to the top, you're going to have a majority of potential energy. And since the speed is just starting to build up, you'll have not so much kinetic energy. The closer you get to the bottom, you're going to have only a little bit of potential energy left. And you're going to have lots and lots and lots of kinetic energy. Okay? So as you go from top to bottom, the potential energy slowly gets converted into kinetic energy. So one more thing, as long as we're talking about no friction, all right? The speed of a roller coaster and how high it can go and everything like that is dependent on that initial starting height. That's where the higher you are to begin with, same thing like with like a bobsled race or with a ski race, or anything that involves going down a hill. The higher you start from, the more energy you will have to work with to get all the way down to the bottom and keep going, okay? There's also the fact that the height that you start with is your max height. You cannot get higher than that without putting in some more work to get you going, okay? So this roller coaster, if it's frictionless, the car can get back up that hill. But say instead of starting at that height, say the roller coaster starts here. Could the roller coaster get over there? Hopefully you're saying no. All right? So just keep in mind the relationship between mechanical energy, kinetic energy, and potential energy, where you have your potential energy, how it's related to the height, where you have kinetic energy, how it's related to velocity. And in class, we'll start working on some problems with this. Make sure you do the online form and bring some notes.